So good evening, everyone. I hope I'm audible and visible and my screen is visible as well. Okay, so welcome to today's live session of Nonlinear Vibration, NOC25 me57. And this course is being taught by Professor S.K. Dwivedi. And I'm Rasha Diti Ranjan, NPTEL PMRFTA. And we'll be talking about, or we'll be taking the questions related to whatever was covered this week so that it will be helpful for you to solve the assignment problems. So, firstly, I'll give a brief discussion about what was discussed in the lecture. So, okay. So this week was all about the solution of nonlinear equations and how can we obtain the solutions. Okay, so as we have discussed earlier also, I'll just give a brief idea that the solution of a nonlinear equation, what could be the possible solutions of a nonlinear equation? So there are four possible solutions. First one being the fixed response. Fixed response means, for example, there is a damping present in the system and there is no forcing, any kind of forcing inside the system. In that case, whatever be the initial condition of the system is going to come back to the fixed points, right? Whether be it the stable fixed point or unstable fixed point, anyways, it will attain the same stable fixed points. So that is the fixed point response. Okay. So second one is the periodic response. Periodic response means what? There is a periodic motion. Okay. So after a certain time period, the response is being repeated. Okay. Third one is the quasi-periodic response, wherein we have we have a kind of irrational ratio between two frequencies, right? There we get the quasi-periodic response. And the last one is the chaotic response, which we have discussed. That chaotic response is essentially a type of aperiodic response, wherein there is a strong dependence on the initial condition. And we have discussed in the last week's live session, I guess, that in case of a fixed periodic and quasi-periodic response, specifically in case of a periodic and quasi-periodic response, the response actually depends upon the parameter value and it does not show a very strong dependence on the initial condition. Like we did some numerical experiment last week that wherein we were changing the initial condition and we saw that the response was the same. The steady state response was always the same. However, in case of a chaotic response, what we saw was that even for a very small variation of initial condition, if you remember, I think we did for 10 to the power minus 4 to minus 6 maybe. We did the experiment that even for a variation of 10 to the power minus 4 or 10 to the power minus 6 in the initial condition actually changes the system response very drastically after a certain time period, right? So that is a chaotic response. Okay, so now we know what could be the possible solution of a nonlinear equation, right? But now the question is, how will I obtain the solution? One is the numerical method, we know. Yeah, one is the numerical method that we know. Okay, now there are various kind of numerical methods, like you have the Euler method, right? You have the RK method, you have the RK4 method, right? These are the possible numerical methods that can be used, right? And all these methods are actually based on the concept of geometry, wherein we say that, for example, this is my curve of a system. Okay, this is the curve. This is the plot of x versus f of x, right? What do we know in case of a differential equation? We know the function. Mm, let us say we have some g of x, right? Now, in that case, which is essentially the slope of the function, right? Now, this is essentially df of x with respect to dx. Okay, so if you see on this graph, it is essentially the slope, right? So if I have this point, okay, which is essentially my initial condition, I have x naught and I have the value f at x naught, and I know this slope, then I can calculate this value x1, isn't it? What will it be? See, I have the slope for a right angle triangle. This is the perpendicular, this is the base, this is the hypotenuse, correct? Now, if I know that what is the slope, yeah, then I can use this concept in order to get what? For this b, I can get the value of p, right? If I know the slope, what do I have? This is theta. I know tan theta, right? So I can get this value, right? So this is a zoomed view, okay? So if I know this value, p, right? So what will be the value of this point, f at x1? It will be nothing but f at x1 will be nothing but f of x naught plus p, correct? Which we can take out by using what? By using the slope that we have, right? Now this is simply the Euler method. Now this is a numerical technique. Okay, if I want more accuracy, I want better solution, so I'll try that my value of b is very small, right? RK4 uses the same concept. The only difference is that it evaluates the slope or the value at 4 points and then it takes out the weighted average. Okay, you can go and study in any of the numerical methods book of mathematics that what is the concept, exact concept of RK4 method. However, the main thing is similar to the Euler method, the RK4 method also uses the concept of slope. It evaluates the slope at 4 points. It evaluates the value at 4 points and then takes out the weighted average. Okay, to get better accuracy, definitely. Right. Now, numerical method is fine. But we know that if we have an analytical solution, it is much easier for us to, predict the solution or to know where to operate my system. Right. So in that case, some researchers tried that, okay, maybe we should do something to get the analytical solution. But getting a proper analytical solution for a for a nonlinear differential equation is difficult. Okay. So some analytical methods were introduced that give us the approximate solution. Okay. It essentially gives us an approximate solution. Like for example, if I say, let us talk about a Duffing equation, okay, or any kind of a spring mass system that has a dashpot. So we know that whatever be the, initial condition, if a forcing is applied on it, the initial transient is going to fade out, and then we are going to get a periodic solution, right? So these approximate solution. Now, if we are using the numerical method, we are going to get the whole trajectory with time. But if we want to get an approximate solution, since we want to work only on the steady state solution, then we can use the approximate analytical solutions, right? Because it is more reliable. definitely. It gives us a better approach to know about the solution. Okay, but it is limited. It is not giving me the whole response. It is giving me the response either with a pre-assumption or by considering some perturbation or that kind of a thing. Right. So that is what analytical solution is all about. Now there are various kind of analytical, approximate analytical methods. Like we have the straightforward expansion, we have the harmonic balance method, we have the incremental harmonic balance method, Lindstedt-Poincaré method, likewise, method of averaging, different kind of solution you can get. Then we have the perturbation method, wherein we basically perturb our system by a very small amount so that we can finally get a linear equation that it will satisfy, and then we can analyze the system. Okay, I hope it is clear. Anyways, everything was discussed in a proper way, in a proper expanded manner in the lectures. Okay, so we'll start taking up the questions. So coming on to question number 1. So question number 1 says that for a 2 degree of freedom spring mass dashpot system, how many first order differential equation is required to get its response from ODE45 or RK4 method? Okay, so the RK4 method in MATLAB, it is used as ODE45 command. Okay, so first we will see about the 2 degree of freedom system. So we'll have a spring mass M1. Okay, so last week we already discussed that how can we find the equation of motion. I hope that is clear. We had various methods. We had the force balance methods, then we had Newton's second law, then we had this essentially force balance method is Newton's second law. We have energy methods, which has Lagrange equation and the Hamilton's principle. Here I will not get much into how to define the equation of motion. We'll just briefly derive the equation and then see that how to tackle with this problem. See, along developing a equation to solve is a task. Okay, we developed an equation that would tell us about the equation of motion. It would tell that how the system will behave. But until and unless we don't get the solution, there is no point of finding the equation of motion, right? So finding the equation of motion is important, but finding the solution is as important, right? And that is why it is very important that we understand how should we use the methods of finding the solution. Or even if we are using the numerical method, how should we use the numerical method, right? Because in numerical method, since you have seen, it is also approximating the value, right? It is converting my continuous system into a discrete system, right? So it can give error. For example, at one step there is a very small error, but if I apply 1,000 steps, that small error is going to multiply by 1,000 times, right? It will become a very massive big error which we cannot afford, right? So it is very important that you understand how should we apply the numerical methods. Okay, so if this is a mass, here it is x1, x2. Okay, so here there will be a force k1 x1, c1 x1 dot, k2 x1 minus x2, c2 x1 dot minus x2 dot, and there will be a inertia force m1 x1 double dot. So from here we are going to get the equation of motion as this is my first equation, correct? Similarly, if I apply for the second mass, which is m2, So we'll get the equation of motion as these two will be my equation of motion. The spring force, it is given nonlinear for this question, but I suppose that you people can now solve this. I don't think that it is an issue for you if you want to consider the nonlinear spring force. I think you people can do it. I have discussed it in the previous live session also, that if there is a case wherein you have to find the equation of motion considering the non-linear effect of the spring, then what you are going to do, you are going to find the solution for the linear equation, right? And then you are going to replace the spring force with the non-linear force. Okay, so I'll not get into that this time. We'll simply find what the question is asking. Okay, so these are the two equations that we have. Now, in order to simulate it with the RK4 method or the OD45 method, now I told this earlier also in the previous week and during the starting of this session, that the numerical method essentially considers the first differential, right? So if I'm telling OD45 or RK4 method that okay, I want a solution, so I have to give in the input, I have to give in the input in the form of a differential equation. Correct. I have to give in the input in form of a differential equation, but a first order differential equation. A first order differential equation. The RK4 method directly cannot evaluate the second order or higher order differential equations. Okay. So what am I supposed to do? I'm supposed to convert my higher order differential equation into first order differential equation. So every, like if I have a nth order differential equation, I can convert it into n first order differential equation. I can convert it into n first order differential equation. So here I have the second differentials of x1 and x2 both. So what will I do? I will now try to convert both into first order. Okay, so what will I do? I will assume that I have a variable z in MATLAB or even in RK4 if I do it numerically by my hand. Z, which is an array. Z is an array which constitutes my x1, x1 dot, x2, x2 dot, right? Because x1 double dot, x2 double dot, I already have an analytical equation. That is what I have to integrate to get the solution, velocity and displacement. So I will assume that my z is a variable like this. In that case, I have to define a z dot, which my ODE45 or RK4 method is going to integrate, which will constitute x1 dot, x1 double dot, x2 dot, x2 double dot. Correct? This is what I'm supposed to do. Now, what will I do? I will assume my z of 1 as x1 dot, z of 2 as x1 double dot, z of 3 as x2 dot, z of 4 as, okay, wait, correct? What will happen? If I'll integrate this, the integration will give me z1 as x1, z2 as x1 dot, z3 as x2, and z4 as x2 dot. Correct? I hope this is correct. This is clear to you all. Okay, this is how you are going to embed it in the system. right? You write it like that. Okay, so you will define essentially z dot in terms of what? Z1, Z2, Z3, Z4, right? Like you'll have to define z dot as, I have x1 dot, which is what? X1 dot is Z2. So I'll write Z2, semicolon. Then what is x1 double dot? X1 double dot, I'm going to have here. Have a equation of x1 double dot, which I can get from here. From here I can get x1 double dot, some f1, x2 double dot is f2. So here I'll put f1. Then I'll have x2 dot. X2 dot is what? Z4 and f2. And this I'm going to integrate. Do it by RK4 method. You can see what the equations are. You can do it manually also. However, manually it is very difficult because for every iteration you have to apply 4 steps, calculate the value, calculate the weighted average, and again go to the next iteration. Okay. You can use OD45 directly, or what you can do is you can make the RK4 methods algorithm in MATLAB. It's very easy. If you want, you can try. Okay. So how many first order differential equations is required? 4. Simple. And likewise, depending upon your equation, depending upon the number of equations you have, the kind of differentiation you are having, you can find out that how many you have to define. I hope this is clear to all. This was very simple. Okay, now coming on to question number 2. Uh, okay, I'll first consider a linear equation. You can simulate it on your own also. If you consider a simple spring mass system, linear equation, which is mx double dot plus kx is equals to 0. I want you to simulate this. Okay, if you simulate this equation for like different initial conditions, you will get that whatever be the initial condition, the system is going to have different amplitude because of the initial condition, but the frequency of oscillation is always going to be the same, which is nothing but the natural frequency of the system, right? So whatever be the initial condition, the frequency of oscillation will always be the same, right? However, the amplitude will depend upon the initial condition. Okay, now we consider a nonlinear system. My Duffing equation is nothing but what? Extension of a spring mass system considering the nonlinear effect of the spring. Okay, so if I consider a Duffing equation, if I consider this is my Duffing equation. Okay, now if I want to find a relation, or if I want to know whether my amplitude or frequency has a relation or is it independent, whatever is it, I don't know by barely just seeing the equation of motion. I cannot predict anything, right? So what can I do? First way is I go to the MATLAB and I try to simulate the system for different initial conditions, right? Then I will get to know whether the frequency is dependent or not, right? But no, I want to find it analytically. For example, I don't have MATLAB. I don't want to solve it numerically. I want to solve it analytically. So what will I do? First thing is, I assume that my response is what? Periodic. First thing is I assume response is periodic, which means we assume solution. We assume the solution as what? A cos omega t plus beta. This I can call it as phi. I've assumed my solution that it is periodic and it is of this form. Okay. Now I know the expression of x, so I can evaluate x dot or x double dot x square x cube and I'll put it in the main equation, right? So let us do that. X dot is what? Omega minus sine phi, and my x double dot is what? Cos phi. This is clear, I guess. Simple differentiation. This is simple differentiation. Now, I have to evaluate x square, which is nothing but a square cos square phi, right? Now by trigonometry, I know cos square phi is equals to what? It is nothing but 1 plus cos 2 phi by 2, right? I'll use this expression. So I'll get a square by 2, 1 plus cos 2 phi. Okay. Similarly, I have to evaluate x cube also. Now by again, I'll use trigonometry, which says cos cube phi is nothing but 1 by 4, 3 cos of phi plus cos of 3 phi. Okay. Again, this I can use and I'll put it here. So a cube by 4, 3 cos phi plus cos of 3 phi. Okay. Now I'll use these, putting this in main equation. Let us call it as 1. Hello, am I audible? Okay, so putting this in main equation, what will I get? Sorry, let us add a slide. Okay, putting this in main equation, I'll get minus omega square a cos of phi. Then I had what? Omega naught square a cos phi. Then I have alpha 2 x square plus alpha 2 x square is nothing but a square by 2 1 plus cos 2 phi. And then I have alpha cube a cube by 4 into 3 cos phi plus cos 3 phi. 3 cos phi plus cos nonc25 is equals to nothing but 0. Okay, now see, for now I will neglect the higher order term. Okay, I will neglect the higher order term, and what will I try to do? I will try to equate what? The coefficients of cos phi. Okay, I will try to equate the coefficients of cos phi. So if I equate the coefficients of cos phi, comma, we get what? Minus of omega square a plus omega naught square a plus alpha 3 a cube by 4 into 3 is equals to 0. Correct? So what will I get? I will get omega square is equals to omega naught square plus 3 alpha 3 a square by 4. This is what I get, isn't it? Did you realize what I did? So I had one equation of motion, okay, which is of a Duffing equation. I assumed that my solution is periodic. Okay, it is periodic. So I assumed my solution as a cos omega t plus beta, wherein I have considered omega t plus beta as phi. Then what did I do? I found the differentiations with respect to time, which is x dot and x double dot. Okay, I used these expression, and I also evaluated x square and x cube. Then I used these expressions and I put it into the main equation. Okay, which is nothing but this main differential equation. After putting it into the main differential equation, I equated the terms of cos phi, wherein I got what? This equation. So here you can see omega naught is nothing but my natural frequency of the system, right? So if you see that my omega square, which is what? Omega is essentially the frequency of my response. Omega is not the forcing frequency. We are not having any kind of a forcing frequency over here. Okay. In case of a linear system, if we have seen, even if we try to find the analytical solution, we'll see that my solution of my equation is going to give me that my system is always going to vibrate with the natural frequency of the system. Here, after solving the equation, what am I getting? I'm getting that the oscillate. First, I've assumed that my solution is actually, or my system is vibrating with the frequency omega. Then I put it into the analytical solution. So I get that my omega, which is the frequency of the solution, assumed frequency, is actually not exactly equal to omega naught square. It is not exactly related to omega naught square. It actually depends on the amplitude as well. A, amplitude of oscillation. It will depend upon the amplitude of oscillation. So by this equation, what do we get? We get that my omega is not independent of the amplitude. Okay, you can change the amplitude. For example, if I keep my initial velocity 0 and I keep my initial displacement as 1, it is going to have a different kind of a frequency. If I change it to A2, what will happen? My frequency is again going to change. Frequency of oscillation. Something will get added with the natural frequency of the system, and then that would be the solution. Okay, so it will keep changing with the initial condition. The oscillation amplitude, the oscillation frequency of the solution, it will keep changing with the amplitude. It depends upon the amplitude, right? So what can we see from here? That just adding small non-linearities to the spring mass system, the oscillation frequency now depends on the amplitude of oscillation. It is now not independent, which we saw over here that it is independent of the amplitude, or it is independent of the initial condition. But as we add these two terms of nonlinearity, we see that my oscillation frequency now depends on the amplitude of oscillation, right? It will change. Okay. So also what is important to see over here, if alpha 3 is equals to 0, my omega will be equal to omega naught, which means that if my nonlinearity is not present, then in that case my oscillation amplitude and the natural frequency is going to be the same. That means my system is always going to oscillate with the natural frequency of the system. Okay, so from here we get the frequency of oscillation omega depends on the amplitude of oscillation. I hope this is clear. Okay, so for question number 2, the answer will be depends on the amplitude of the response. Okay, I hope this is clear. And you can check it numerically also. Like after this session, maybe you can write a code for the Duffing equation. You can consider either x square or x cube, whichever you want, and then maybe you can try that how it is changing. Okay. 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 There's one more thing I want to mention over here. The method by which we found this solution, it is nothing but the harmonic balance method. Okay, this is the basic concept of the harmonic balance method, wherein we assume a solution, we put the solution in the main equation, we then equate the coefficients on the left hand side and on the right hand side, from where we get a relation between the coefficients, by which, like here we assumed a solution. Okay, we had a, we had omega, we had beta. So by equating the equations on the left hand side and on the right hand side, we are going to get the expressions, or we are going to get the value of a, omega and beta, and then we can get the solution. So similar concept, we have this question. For the force Duffing equation, use harmonic balance method to obtain the relation between the frequency and amplitude. Okay, so in the previous question we had a free system. Free means it was not having any kind of a forcing present. Now we assume that for the forced Duffing oscillator. Okay, so we'll assume for the forced Duffing equation, we assume our equation is x double dot plus x beta x cube f cos omega t. Okay, again what will we do? Assume x is equals to a cos omega t plus b sine omega t. We'll find the differentiation. X dot is equals to it. This should be cos and this should be sine. Yeah. Okay. Further, we also require x cube. Okay, which is a cos omega t sine omega t whole cube. So by using the a plus b whole cube formula, we can have this b cube sine cube omega t plus 3 a square cos square omega t into b sine omega t plus 3a cos omega t b square sine square omega t. Okay. Now you can further use the trigonometric identities of all these for the cubic terms and for the cos square sine and sine square cos terms. Okay, and I'm skipping that step as of now because it will take our time. There's no point of discussing that. You can go through that. Okay, so we'll get something like cos omega t plus 3 by 4 b a square plus b square okay. We are going to get the higher order terms, but we have assumed that my solution is periodic and it is something of a cos omega t plus b sin omega t type. We are not considering the higher harmonics as of now. Okay, so we are neglecting the higher order terms as of now. Now we have the expression for x dot, x cube, x double dot. We are going to put it in the main equation. This one. What are we going to get? We are going to get minus of a omega square cos omega t minus b omega square sin omega t x plus a cos omega t b sin omega t beta x cube, which was 3 by 4 plus b a square plus b square sin of omega t is equal to f of cos omega t. Okay, so this is the expression that I will get. Now what will I do? By the concept of harmonic balance, what will I do? I will balance the harmonics on both sides, LHS and RHS, right? Because if the LHS is equal to RHS, this is possible only if the coefficients of cos terms and the coefficient of sine terms can be related, right? So balancing the harmonic terms on the left hand side and right hand side, right? What are we going to get? We are going to get two equations because we have a cos omega t term and we have a sin omega t term, right? So what will we get? So by balancing the cos omega t terms first, I'll get minus a omega square plus a plus 3 by 4 beta a a square plus b square is equals to f. Correct? This is my one. Then I will balance the sine omega t terms. Then I'll get minus of b omega square plus b plus 3 by 4 beta b a square plus b square is equals to 0. This is my second equation. So first I will look into the second equation. Why? Because my RHS is 0. So I can essentially get some value from it. Okay. So what will I have? I can take b common. Then I'll have 1 minus omega square plus 3 by 4 beta a square plus b square is equals to 0. Okay. Now one solution could be b is equals to 0. One solution could be b is equals to 0. But that is not possible because we have considered that my solution is of the kind a cos omega t plus b sin omega t is equals to 0. Right. So that is not possible for me. That I will not consider that my b is equals to 0. So then if b is not equal to 0, then what will I get? I will get an expression. No, wait. Okay. No, no, no. This I cannot consider as 0. This I cannot consider as 0. Do you know why? Because then I'll have to consider beta 0 and omega is equals to 1, which is not possible. So we will consider b is equals to 0. This cannot be equal to 0. So we'll assume let b is equals to 0. As of now, we are just letting it. There could be a possible situation where b is not equal to 0 and this is equal to 0. But as of now, we are considering b is equals to 0. Then, using 1, what will I get? I'll get a into 1 minus omega square and b is 0. So we will have 3 by 4 beta a cube. We'll have plus 3 by 4 beta a cube is equals to f. Yes. Also, why we are not considering this as 0? Because in this equation, if we take a common, na, we'll have a. If I consider this as f, not f, let us say this is g. Then from this equation, we are going to get a into g is equal to f. Okay, so if my g is 0, then this equation does not have any validity. This equation will not exist. That is why we cannot consider my g is equal to 0. Okay, so this will be wrong. Okay, so this is the expression that we get. So this can be further written as a 3 by 4 beta a square plus 1 minus omega square is equals to f. So what can you see? This is essentially, if I know the value of f, if I know the value of omega, if I know the value of beta, this is essentially a polynomial with the order 3, a cube, right? So if I solve this, what am I going to get? I'm going to get 3 roots. I'm going to get 3 roots because a has a power of 3. I'm going to get 3 roots. Now it may happen that among those roots, I can have positive value, I can have negative value, I can also have complex conjugates, right? So if you plot this, what you're going to get is that there exist the values of f, okay, for which my system is going to have sometimes 3 positive values, a, because a is amplitude of oscillation, right? Amplitude is always going to be positive. It cannot be complex, it cannot be negative. Okay. So you are going to have like 3 values of amplitude. If you see the variation, like for example, if you see the variation with the frequency omega, okay. So if you change the value of omega, you're going to get three values of A, and it is possible that at some value of omega, you're going to have only one positive value. At some value of omega, you're going to have three positive values, and again you are going to have one positive value, right? It can happen. The other two values, it could be negative, it could be complex conjugate. Okay, so if you will try to do the numerical experiment, you will get to see that there is this kind of a behavior of the system. If I plot A with respect to omega, I'll have something like this. This is the plot. Okay, so I will see that, okay, let us make an exaggerated view. Looks better. Let's change the color to red. Now we'll see. I have 2 points. One is this point, other one is this point. If I make C, in this region, what do I have? I have three values of A corresponding to a single value of omega. I have three values of A corresponding to a single value of omega. But if I look here or here, there exists only one value of A corresponding to the value of omega. Now this is what we call as the jump phenomena. If you'll see in a system that for a physical system, like for example, initially the value of omega is 0, and now you start increasing the value of omega very slowly, you will observe that as the value of omega increases, the amplitude increases. The amplitude increases slowly, slowly. You'll see that it will follow this path, right? It will keep following this path until where? Until here. After this is not going to follow the curvature. But what will happen? It will just drop down immediately, and then it will start following this path. It will start following this path. Okay, so what is going to happen? So what is going to happen is this. This becomes an unstable solution. Okay, the system is going to jump from this point to this point, right? Now this is essentially what? This is the jump phenomena. Same is going to happen if we go from a higher value of omega to a lower value of omega, right? In that case, my system will follow this path. After reaching this point, further decrement of omega, it is not going to follow the path, but it is actually going to jump up like this, and then it will start decreasing. Okay, so system essentially jumps from this point to this point. Okay, so this is essentially what we call it as a jump phenomena, and this you are going to get for a nonlinear equation. This was a very simple equation. If you see the equation, this was a very simple equation. Very simple. Just a bit of nonlinearity in terms of x cube, beta x cube. That's it. Okay. Now here I have considered that my system is not having any kind of a damping. Okay. What if my system has any kind of a damping? What if my system is going to have some damping? Then what will happen to the expression? If my system, if damping is present, then my expression will become something like this. Okay, we have introduced a damping term. We have introduced a damping term, right? Again, by the similar method of harmonic balance which we used earlier for the undamped system. Similarly, we are going to assume the same solution, a cos omega t plus b sin omega t. We are not going to change the solution. The only thing is that now the expression has changed, but the assumption is same, that the solution is periodic and it is of the form a cos omega t plus b sin omega t. Okay, so we will again find x dot, x double dot, the expression for x cube, and we will put it in the equation. So I'll write the final equation which we are going to get after equating. Okay, so we assume the solution of the form a cos omega t plus b sin omega t, finding the expressions for x dot, x double dot, x cube, and putting it in the main equation of motion, comma, we get, okay, putting in the equation of motion and further equating the harmonics on LHS and RHS, we get, I'll be writing the equation. If you want, you can, after the live session, you can maybe try evaluating the expression. However, it is a hectic task, but if you'll try, it will be better for you. Okay, plus b plus 3 by 4 beta b a square plus b square minus is equals to 0, and a omega square plus a plus 3 by 4 beta a square plus b square minus epsilon omega b is equals to f. This is what I'm going to get. Okay, I hope this is clear. Now what will I do? I will try to do something that I did last time, but see, that is not going to work over here. Yeah, last time what we did, we take b as common and we assume b was equal to 0. But this time we don't have a b here. We don't have a b here. So what will we do? We will multiply this by what? We will multiply this by, okay, we can multiply, or what we can do, we can apply square also, because that will help us. Yeah. Okay, we can write these equations as b minus omega square plus 3 by 4 beta a square plus b square. This we can put in a bracket, minus omega a is equals to 0. Then we can write as a 1 minus omega square plus 3 by 4 beta plus, there should be a plus over here. Yeah, good. Okay, so we will just assume what? We will assume that this expression is d. Just for the simplicity of calculation, we will assume that this is d. Okay, so my equation will become what? My equation will get simple now. I'll have b into d minus sin omega is equals to 0, and b, no, a into d. A into d plus sin omega b is equals to f. Correct? Squaring on both sides and then adding. What will I get? I will get d square a square plus b square. Okay, maybe I should not skip this step. B square d square plus sin square omega square a square is twice of b d omega a plus e square d square omega square b square minus a d omega b is equals to f square. This both will get cancelled out. So I'll have d square into a square plus b square. Then I'll have plus omega square into a square plus b square is equals to nothing but f square. Now in my previous expression also, where I considered this term as d, I have this a square plus b square term. So I will assume, if I have a expression of the form a cos omega t plus b sin omega t, if I have this, then my amplitude of oscillation is actually under root of a square plus b square, isn't it? So if I'm getting an expression which is of the form a square plus b square, I'll maybe utilize it. I will assume a square plus b square is gamma. Okay, now my expression becomes a bit easy. Yeah, now I have gamma square, sorry, gamma, not square. Okay, maybe we can assume as gamma square, because if my amplitude of oscillation is gamma, this is gamma square. So gamma square into d square plus this square is equals to f square. Now from here, if I have a value of omega, if I have a value of f, what I can do? I can actually get the relation of gamma. Yeah, I can get the plot. Let us just put the expression for d square again. Okay, I have 1 minus omega square plus 3 by 4 beta gamma square. Yeah, here it was a square plus b square. So we'll write it as gamma square, this whole square, plus this is my expression. Now I can select a value of omega or f, and I can now plot that how my system is going to behave, right? And I can get a plot for gamma, right? Where gamma is nothing but my amplitude of oscillation. Okay, so this is how you can tackle this problem. I hope that this is clear. See, this is the basic concept of harmonic balance, okay, wherein we assume that my steady state solution is periodic, and then we use that expression of periodic solution, and then we find the expression of whatever the, like for a cos omega t plus phi, we have to find the expression of value or expression or value of a omega phi. So we can put it in the equation, and then we can equate the harmonics, and we can get the solution. Okay, so whatever the example we have considered over here, we have just considered the, like, the main harmonics. We have neglected the higher harmonics, and it is fine also. There's no issue with it. Okay, let us now come to question number 4, which introduces the concept of secular term. Okay, so when we are solving a differential equation, we try to make the secular term equal to 0. Okay, why do we do this? I will try to explain you with this example. Okay, see, I have a differential equation of this form. Okay, this is my differential equation. Now, if I talk about the solution of a linear differential equation, what is it? Solution of a linear differential equation. It is nothing but complementary function plus particular integral, right? If I want to find the complementary function, I can simply find it by this equation. Here I assume that my u1 double dot plus k u1 is equals to 0. From here I get the solution, okay, which is the complementary function. But I want to find the particular integral, okay. So if my expression on the right hand side is of exponential form, right, then I have a formula for calculating the particular integral, right? So I can write this as what? I can write this as d square plus k into u1 mt plus, this way I can write. Okay, so by the formula, if my f of d into y is this, okay, is this f of d into y is equals to a to the power e to the power ax. My complementary function, I don't think I need to discuss. We'll just work on particular integral. My particular integral is going to be what? E to the power ax divided by f of d, where d is equals to what? A. Okay, f of a. This is going to be my particular integral. Now, what if f of a is equals to 0? Then my particular integral is going to be x e to the power ax divided by f dash of a. Okay. Now this, if you see, is fine. If I consider x as time, this is fine. Okay. If we'll write in terms of time, it will be something like at divided by f of a. Second case, I have e to the power at f dash of a. Now in terms of time, this is fine. Okay. But if I talk about this, what is happening? Yeah. Okay. There has to be a minus over here that I've missed. Yeah. There should be a minus since we are considering this for this equation. This is fine. Why this is fine? Because with time, this is a negative exponential, so with time the value is going to decrease anyways. Yeah, the value is going to decrease. However, if I have this expression, what is going to happen? My exponential term is going to decrease with time, but my time is increasing and it is in multiplication with the term. Right. So what is going to happen? What is going to happen? See, this is going to create a problem. Yeah, this is going to create a problem because as time tends to infinity, a particular integral also tends to infinity, which is not possible since we have already assumed that my solution is going to be bounded. Right? We are not working on infinite solutions. See, in case of chaos also there is a very beautiful property of chaos, that chaos is always bounded. It can never go unbounded. It can never go to infinity. This is a very beautiful thing about chaos. We don't know how the system is going to behave. We don't have a periodicity in the system, but my chaos is always bounded. My chaos is going to give me a bad kind of a solution. It does not give me the required solution, but it does not take my system to infinity. Right? So even if I have a nonlinear system, it is never going to have an unbounded solution. Right? So if I have terms of this sort, okay, if I have terms of this sort, then what is going to happen? It is going to give me a solution which is not possible physically. So when we are going to try the approximate solution, we are going to find the approximate solutions, it is very important that we keep in mind that we have to anyways avoid any kind of a secular term. Yeah. So that is what we are doing over here. So in case of a secular term, what should happen? So see, for here, for particular integral 1, what are we going to have? We are going to have a e to the power divided by d square plus k. Here we have to replace, sorry, I'll skip this step. We just replace d with what? M and I, right? We'll have minus im square, right? Actually, we should not consider minus over here. We have just taken an example, it's fine. We are just concerned about the secular terms, okay? We'll not consider the minus. We'll just consider im square, okay? Now, if I take the square, what is going to happen? Let us just consider this. I is iota imaginary value, so its square is going to be minus nm square. So we have k minus m square is equals to 0. If you want to have the secular term, this should be equal to 0. So my m should be equal to what? My m should be equal to what? Plus minus under root of k, which is not in the solution, which is not there in the option. Okay, but we have to have a correct answer. Then what is the correct answer? Okay, so there is another exponential term also, which is this one, right? Which is this one. So in this case, what is going to happen? What is going to be the denominator in this case? Denominator is going to be nothing but d square, replacing d by this. We have 3i square. Denominator is equals to this plus k. So in order for the secular term to exist, we have to do this. This will be nothing but k minus 9 is equals to 0. K is equals to 9. So if my value of k is 9, this will contribute to the secular term. So this is the correct answer. Okay. So you have to apply this concept if you want to find like how to avoid the secular term. Okay. Now coming on question number 5, this is a theoretical question. I thought that I'll just briefly discuss it. Okay. So we will take the points by point and we will discuss brief about everything. Okay. So the first one is in the straightforward expansion, the response is expanded by the use of bookkeeping parameter, which is true because in case of straightforward expansion, we assume my solution x is essentially written as, okay, so x, which is a function of t and parameter this, the bookkeeping parameter, is written as x naught plus x1 plus the higher order terms. So my first expression is absolutely correct. Okay. Here I assume that my solution can be written in an infinite series like this. We can consider the finite number of series as well. Anyways, when we are doing the approximate solution, we are finding a proper approximate analytical solution. We consider that like till a certain number of expansion, like 3, 4, or maybe 10, if we are using like MATLAB for solving the equation, right? The second is in the Lindstedt-Poincaré method, only the frequency of the response is expanded using the bookkeeping parameter, which is wrong, right? Because in that method, sorry, in the Poincaré method, we assume that this is constant, that we assume that my solution is expanded, can be written in an infinite series form like this. This is constant, but along with the concept of straightforward expansion, since in case of straightforward expansion we had the problem of having many secular terms, so we tried having another method by which we can actually reduce the effect of that. We assumed that my omega is also written in terms of an infinite series, okay, and then we use both these expression to find the approximate solution. Okay, so this is wrong because it writes only the frequency. That is not true. We assume that the frequency and the response both are expanded in terms of an infinite series. Now the third option is in harmonic balance method, the harmonics are balanced to get the solution, which is true. And we have already done 2-3 examples considering the harmonic balance method, isn't it? What do? We assume the solution, we use the assumed solution, and we put it in the main equation, and then we equate the harmonics in order to get the values of the assumed solution parameters, right? And you see that for the harmonic balance method, it is, why do we actually assume the solution in cos and sine form? You know why? Because even if we have higher order nonlinearities, the nonlinearities can again be converted into sine and cos forms, right? And then it becomes easy to equate the parameter values. Okay. Now the fourth option says that all the above mentioned methods give the exact solution of the nonlinear system. Okay, so this is absolutely incorrect, right? Because for a nonlinear system, getting an exact analytical solution is difficult. It is not impossible, it's difficult, right? You can get an exact analytical solution, but all the methods that you have studied this week, they are essentially approximate methods, right? In those methods, you have assumed that the solution can be written in terms of expanded series by using a bookkeeping parameter. Yeah, or you can maybe assume that my system in the perturbed form, right? We assume that corresponding to equilibrium state, my system is perturbed by a very small amount. Or we can use the harmonic balance method, but there also we ignored the higher harmonics and we assume that my solution is periodic, which is not true, because in case of a chaotic system, we can have periodic, we can have quasi-periodic, we can have chaotic. Okay, and chaotic is aperiodic, then how will we find the solution? Okay, so this is essentially wrong. The analytical methods that we are studying can give me an approximate analytical response, but it does not give me the exact solution of the nonlinear system. Okay, I hope that this is clear. Coming on to question number 6. Okay, we have to find which of the following options is correct, right? If we assume the solution which is given in this form. Okay, we will do this. So our first approach will be to write x and find x dot, which will be nothing but 2b1 x double dot minus 4b1 sine of 2t. Okay, this is clear. Apart from that, we have x and we have x cube. So we will have to find the x cube, which will be a naught cube b1 cube sine cube 2t plus 3 plus 3. Yes, okay. Now again, what will we do? We will assume the expression, sorry, as not assume, we will use the we will use the trigonometric identities. So sine square theta is nothing but 1 minus cos 2 theta by 2, and sine cube theta is nothing but 1 by 4 3 sine theta minus sine 3 theta. We will use these two identities in this, and then we will get x cube is equals to nothing but a naught cube plus twice of a naught square b1 sine of 2t yeah 3 1 by 4 sine of 2t minus b1 cube by 4 sine of 3 into 260 and twice of a naught b1 square by 2 minus a naught b1 square cos of 4t. Yeah. So what will we do? Neglect the higher order terms. We will neglect the higher order terms and then we will put it in the main equation. Putting the given differential equation, comma, we will get minus 4b1 sine of 2t. We have 0.1 x dot. Yeah, so we will get plus 0.2 b1 cos 2t. Then we have a naught plus b1 sine of 2t plus 0.2 a naught cube plus 3 by 4 b1 cube sine of 2t plus twice of a naught square b1 sine of 2t a naught b1 square, and this will be equal to sine of 2t, which is given in the expression. Now what will we do? By the harmonic balance method, we will first equating the constant terms. What are we going to get? So constant term, we have a naught, and we have 0.2 a naught cube, and we have plus 0.2 a naught b1 square is equals to 0. Okay, this is my first expression. Yeah, and if you see in the option, this is what you are getting. Yeah, so this statement is going to be correct. See, it is the same. Now we will equate the coefficients of sine 2t. Correct? Now if we equate, what are we going to get? So we will have minus 4b1, this one, then we have b1 plus b1, then we have this 3 by 4 into 0.2, which will be nothing but 20 plus 3 by 20 b1 cube, and then we will have this 2 into 0.2 which will be nothing but 4 by 10 or 2 by 5. 2 by 5 a naught square b1, and this will be equal to 1. Correct? This is what we got. This I can write as minus 3 b1. Let's check what is the expression. Yeah, minus 3 b1, 3 by 20, 0.4 a naught b1 is equals to 1. So this expression is also matching with what we got. Okay, so what did we do? We just applied the method of harmonic balance on the equation. Okay, we evaluated the expressions, then we put it in the main equation, differential equation, and then we equated the coefficients of the harmonic terms and the constant term, and we got two expressions, right? So this is done. Coming on to the question number 7. Okay, this is again based on the concept of secular term, but earlier we considered the exponential term on the right hand side. Here we consider the trigonometric terms, right? Because whenever we are solving the equation, or we are solving any kind of nonlinear equation with the like straightforward expansion or Lindstedt-Poincaré method, there we assume the solution in the form of a like a series using the bookkeeping parameter. So we use the series in such form that the first expression that I'm going to get, it is similar to that of a like spring mass system, like mx double dot plus kx is equals to 0, right? So what we are going to get, from the first expression, the solution is always going to be periodic, a cos omega t plus phi. Now when I come to the second expression, it always has a term of x1. So if I use that over here, I'm going to always have a trigonometric term, right, along with the differential equation. So I'll have to find a particular integral corresponding to that and then get the solution, right? Now first let us go through the concept, okay, which says that for f of d into y is equals to sine of ax, if I have something like of this form, okay, my particular integral is going to be sine of ax divided by f of d, wherein I have to replace d square by minus of a square. I have to replace d square by minus of a square. Again, if my f of t at d square replaced by minus of a square is 0, then my particular integral is nothing but x into sine of ax divided by f dash of d, right? So if my x is time, which in this case is time, right? It is time. We are actually studying the dynamics with respect to the time. Okay. So my particular integral will be what? It will be something of the form t sine of at whole divided by f dash of t. Now see over here, what are we going to get? As t tends to infinity, this goes to infinity, which is not true because we already know, or we have already assumed, or that is only possible that my system is bounded. The response of my system is essentially bounded. So why is this giving me such kind of expression? So that is because we have assumed the solution, and that is why we call it approximate analytical solution, because we have assumed the solution of this form, right? So if the expression is of this kind, it is actually giving me a wrong solution. It is actually giving me a wrong idea about my system dynamics. So in that case, I try to avoid such kind of a terms if they exist. Okay, if they exist, I try to avoid them. How will I avoid them? So I will avoid them. How? I'll tell you. Okay. So first we will check that which term in the given expression can give me, this kind of secular term, or it is going to give me such kind of infinite solution. Okay. Coming on to this expression. This I can write as how? I can write as t square plus 1 into x2. Okay. So if my d square is minus 1, then that term will give unbounded solution and should be removed, right? So I have to check. Now see, if I see over here, I have cos t and cos 2t, right? So here, if I was having some coefficient, it's square. Okay. So here 2, there is 2. So square of 2 is going to be 4. It will not be equal to minus 1. But here I have cos of t. So the coefficient is essentially 1. Square and taking negative, we are going to get d square plus 1 will be equal to 0. So this is going to be my twice of omega naught omega 1 cos of t is nothing but a secular term. So if this is my secular term, I have to make it to 0. Now how will I make it to 0? Cos of t is not 0. Omega naught, which is the natural frequency of the system, it will not be 0. So what will be 0? Omega 1, right? See, when we are using the Lindstedt-Poincaré method, we are assuming that my omega is equal to omega naught plus this omega 1 plus this omega 2, like this, right? This is how it is, plus till nth orders, right? We only know omega naught. Rest omega 1, omega 2, we have to actually evaluate. How will we evaluate? Using this concept of secular term, right? So now if I want to evaluate, what will I assume? I will assume that my omega 1 is equals to 0. Why? In order to just avoid the secular term, which is very important to get a correct approximate analytical solution. Okay. So omega 1 is equal to 0 and option 1 is correct, right? Similarly, when I come to the second expression, this is of the similar form, d square plus 1 is into x2, right? So, and here we have the cos t term, right? The cos t term means the coefficient is 1, we'll have d square plus 1. We have to replace the d square by minus 1 plus 1, 0. So it is essentially a secular term. Again, what are we supposed to do? Cos t is never going to be 0. So we'll have to assume that this expression is 0, right? Here also, I cannot say my alpha 3 is 0. I cannot say that my alpha 2 is 0. I cannot say my omega naught is 0. Or is it going to have something? These are all given. And a cube also. So what will we do? This will help us to find an expression of omega 2, which again I have to find of omega 2. Omega 1 we have already found out that it is 0. We have to find the expression of omega 2, which will essentially be a function of alpha 3, alpha 2, omega naught and a. Okay, so what will we do? Uh, okay. Omega naught, omega 2a, omega naught, omega 2a minus 3 by 8 alpha 3a cube plus 5 alpha 2 square a cube by 12 omega naught square is equal to 0. This is the best possible way of avoiding the secular term. Okay, so now we will try to find out the expression of omega 2 in terms of all the other parameters, right? So what will we do? We have omega naught, omega 2a okay. So we will take the denominator as 24 and omega naught cube. So what are we going to do? And let us consider a square as common. So we'll have 9 alpha 3 omega naught square minus 12 10 alpha 2 square. That's it, omega 2. So in order to avoid the secular term, we have this expression of omega 2, right? So we'll just see if it is same. 9 alpha 3 omega naught square. Yeah, this is what we are getting. So this is also correct, and the option D is also correct because it says that both A and C. Okay, I hope this is clear. There is nothing difficult with it. Okay, in question number 8, we will now try to solve the equation using the symbolic function of MATLAB, right? Up till now, we were solving it analytically using our own mathematical knowledge, but now we will try to use MATLAB in order to find the solution of this equation. Okay, so right, okay, okay, I'll connect with my laptop now. Stop the sharing. Okay. So this is my expression x double dot plus a1x plus a2x square is equals to 0. Okay, so we'll go on MATLAB. So if you remember, how did we do it last time? First, we'll use the command syms to define the symbolic variables, right? So here we have not taken the value of a1 or a2. A1 and a2 are considered as variables. So we will define it by the symbolic command. So we'll let syms x of t. We have a1, we have a2. Then if we are using the, let us assume that we are considering only till second order. Second order. Okay, we are considering the epsilon and we are considering epsilon square. So we will consider EP as epsilon, and then we have x1, which is a function of time, the first solution, and then we have x2, which is again a function of time, the second solution. Okay. Okay. Now what will we do? We will write the expression of my solution x in terms of the expansion formula. So x is nothing but EP into x1 plus EP square into x2. This is supposed to be my solution by using the straightforward expansion, right? And we have considered only till second term. You can consider up to how many terms you want. Okay. Okay, done. Now what will we do? We will define our differential equation, right? We will write it as DEQ DIFF x comma 2. Now see, we have written x comma 2. We could have written x comma t or something like that. But why we have not written that? So you can specify time also, you can specify the variable also. But since I've already specified that my x is a function of time, so when I'm writing DIFF x comma 2, it is actually calculating the second differential of x with respect to time. Because x is a function of time, so it is just considering the differentiation with respect to the function, sorry, with respect to the time. So DIFF x comma 2 plus a1 into x, and we have a2 into x square. See, we anyways got the solution in terms of x1 and x2. Okay. For example, if I defined my DEQ earlier without defining x as a function of x1 and x2, then I could have used the expand command. Y is equals to expand DEQ. In that case, it would just expand my differential equations. If I put this EP into x1 plus EP square into x2. Right now, what do I want? I want, like, I can get the expressions when I equate the coefficients of EP, then or the expressions which is multiplied with EP, then I want the expression which is multiplied by EP square, and then I want expression which are multiplied by EP cube, something like that. So what will I do? I'll write collect yy, which is my expanded expression. This yy I have just taken as a parameter to define. You can take any of the parameters that you want to define the expanded equation. Like I've considered yy, you can consider xx, or you can write the whole name. That is also possible, whichever you are comfortable with. So we'll do collect yy comma ep. Now if you see what this command has done, earlier this expression of yy, it was actually in a random form. Like there was somewhere it was power of 4, somewhere it was power of 3. There was not a particular order in which the expression was arranged. Okay, but when I have applied collect yy comma ep, if you see my expression has now been specified in a particular arrangement. Like first I have the coefficients or the expression that is multiplied with ep to the power 4, then I have the value that is multiplied by ep to the power 3, then with ep to the power 2, and with ep. Alright, so now from here what can I get? I can get four expressions, four equations that I will further use in order to get the solution. Okay, now this is how you are supposed to uh, define your equation and then get the sorted values, and then you can use the equation. However, I'll just give a brief idea about how you can solve a symbolic equation by using the symbolic commands of MATLAB to get the solution. So for example, I'll consider the first equation, which is the equation that is multiplied with EP. Okay, so I'll define that with DE is equals to, I'll just copy it from here, this term. I'll copy it and I'll place it. Okay, this is nothing but a1 x1 plus diff of x1, which is a function of t twice with respect to t, which is x double dot plus a1 x1. Sorry, x1 double dot plus a1 x1. That is what we got when we did analytically. If you remember, when we did analytically, we used to get something like x1 into omega naught square and into x. Okay, so our omega naught square is nothing but under root of a1 over here, right? That is our omega naught square, which is the natural frequency, right? So I'll define the dE like this, right? Now I know the differential equation. Now I want to find the solution. I can solve it analytically, like on my own on a pen and paper, but I wanted to solve MATLAB to solve it. So I'll use this command y solve of t, which is d solve of d. So I assume my y solve, which is the variable that I'm giving to the solution that I'll obtain, and I'll apply d solve of dE. dE is nothing but the differential equation that I have given. Okay, y solve is the variable that I have given to the solution, and I've applied d solve and have called the variable dE. I'll put OK. Here you can see I got the expression. If you'll closely observe the y solve solution, you'll see, okay, let us first see this. Here if you see, I have something like x1 double dot plus a1 x1 is equals to 0, right? So for this, if I want to find the solution, what will be the solution? So I'll first have to find the roots, which will be d square plus a1 is equals to 0. So I'll have d square is equals to minus of a1, right? D square is equals to minus of a1. So I'll have d as under root of minus of a1, right? So under root of minus of a1 plus minus with a plus minus. So I'll have some solution which will have two exponential terms. One will have positive of under root of minus a1 and one will have negative of under root of minus a1, right? And this is what I'm getting. I'm getting c1, which is a constant of integration, into exp into under root of minus a1 into t, okay, and plus c2 into exp of minus of under root of minus a1 into t, right? This is what I was supposed to get if I solve it by hand, and this is what I got using the MATLAB symbolic function also. Right. Likewise, if I know this solution, now I've got the y sol. Now I'll assume that my x1 is nothing but this y sol. Then I'll put x1 in my second expression, which is this expression, which is the second differential with respect to x2. And then I will further get the proper dE. And then I'll again use the d solve to get the expression of x2. And then what I can do is I know the value of EP, and I can further write my x as EP into x1 plus EP square into x2. And that is how we are going to get the solution. Okay, I hope that this is clear. Okay, now coming on to the last question. Yeah, so this is the Rayleigh equation, and we have to talk about the steady state response corresponding to these initial conditions. So I've already written the code. So this is my code, and I have to take the initial conditions as 1 comma 1. I hope the use of ODE is clear to you all, how we are supposed to use the ODE. We have other ODE commands also, like we have ODE15S, we have ODE23, then we have ODE115, and likewise we have many other ODE options to solve the differential equation, and all these are based on some or the other numerical method, right? So whichever is suitable for your system, you can use it. Okay, and likewise you can also use the DDE command, which is used to solve the delay differential equation. Likewise, you are supposed to solve it. Okay, and if you are not much familiar with DDE, you can maybe just go and search on Google, or maybe search on this command window, from which you are going to get like, if for example I'll write DOC DDE. See, it actually shows the possible DDE ways or DDE commands that may be used to solve the equation that you want. Okay, like solve delay differential equation of general delays. We'll just open it, and then you can see that it tells about the expression, it tells about where it can be used and everything. Okay, so you can maybe search here if you want to solve. Okay, so this is the equation that we have. So we'll have to solve it for 1 comma 1. Okay. Okay, I hope that you can see that this is the phase plot, and this is our time response. Okay, time response and phase plot for the initial condition 1 comma 1. Now if we see what are the other two initial, okay, we have 2 comma 2. So we'll just write 2 over here and 2 over here and run. Now see, what can you see that despite having different initial conditions, the response is actually coming to the same phase plot. However, for the case of time response, there is a phase lag, but the amplitude is same for the oscillation. The frequency is also same. Now this is again the example of a limit cycle. So if you remember, we discussed about the van der Pol equation in the last two live sessions, wherein we talked about the limit cycles, self-excited oscillation, and so this is the similar case. Actually, this is obtained by using the Rayleigh equation, and you know the van der Pol equation is essentially derived from that of the Rayleigh equation only. Okay, so that is why I took this example, that I'll just give this concept that van der Pol equation is essentially derived from the Rayleigh equation only. If you see the expression, it is of this type. Okay, so essentially because of the arrangement of the damping terms, uh, this form, it is actually giving a self-excited oscillation, or we can say an isolated periodic orbit, which does not depend upon the initial condition. So here also, if you change the initial condition, now like I took 2 comma 2, maybe I'll just take 0 comma 0. What is going to happen? Okay, for 0 we have 0. Maybe we can take 0.1 and 0.1. See, for this also it is coming back to the same cycle. Yeah, so be it the initial condition is out of the cycle or whether it is inside of the cycle, it is always going to come back to the same phase plot, see, same steady state response. However, again you can see over here that there is a phase lag. There is a phase lag. Okay, so if we talk about which of the following option is correct about the stages of response of the system, the response is different, the response is same, both lead to the same closed loop, none of the above. So this is going to be the correct answer. We cannot say that the response is same. Why? Because in the time response, there is a phase lag. If it was same, then that could have been other case. Anyways, the transient is anytime going to be different. But here we have to consider only the steady state response. So in the time response, there is a phase lag, but the closed loop is same for both. Okay. So, okay, that is it for today's live session. And I hope that the everything was clear, whatever we discussed, and it was helpful, and it will be helpful for you to solve the assignment problems. And if you have any doubt, you can ask in the next live session. So for now, I'll end the meeting. Okay, thank you.